Hello everybody, this is eDoc2020. Recently I watched Technology Connections video in defense of the CFL, link below, where Alec commented on the lack of decent dimmable CFLs. He guessed dimming was too expensive to put in lamp integrated ballasts, and I'd like to shed some light on this mystery, pun intended. To do that, I'll examine this ballast out of an old three-way CFL. It's not a true dimmable bulb, but it's the next best thing. Stay tuned. I'm not sure how well known three-way lamps are around the world, so let me try to explain. Three-way lamp can switch between three different power levels without using any dimmer circuitry. Here's a standard incandescent three-way bulb. It can switch between 50, 100, and 150 watts. I don't know if you can see that or not. But how does it do this? It's actually pretty simple. This bulb has multiple filaments. On low, it uses a 50 watt filament. On medium, it uses a 100 watt filament. And on high, it uses both filaments for a total of 150 watts. And to do this, three-way sockets have an extra contact to control the extra filament. And on the base of this, we can see here's the extra contact. It's between the tip and the outside screw. Future me here, I figure I should actually show what a working three-way lamp looks like in real life. So here's the incandescent three-way, and I'm going to turn off my bench lights here and then go through low, medium, and high. So this is off, low, medium, high. Do that one more time. Off, low, medium, high. And I should have mentioned that all this is done with a constant exposure on the camera. Now back to the show. So three-way incandescent bulbs are pretty simple, but how does it work in CFLs? But before that, let's talk about regular CFLs first. Most electronic ballast circuits are pretty similar. The mains comes in, it goes through a rectifier, and charges up the capacitor to peak mains voltage. And then there's usually a small toroidal drive transformer, which then drives a pair of transistors alternatively, and that creates a square wave. And the square wave gets sent through a current, gets sent through an inductor to limit the amount of current, and then that goes into the fluorescent tube. And plenty of other people have explained in detail how these circuits work, so I won't go into too much detail now. On the three-way ballast, we see many of the same components, but also lots more. It's like the regular ones. We have main filter capacitors. This one has two because it's a higher power one. We have the drive transformer and a pair of transistors. But we also have many more components. This has two of these inductors or transformers, instead of just one. There are a lot more diodes, and most unusually there's a relay in a light bulb. So to dive into what makes this different, I have some Big Clive style close-up pictures, and now I'll try to reverse engineer the circuitry of this. One moment, please. Here's the complete schematic of the three-way CFL. It's made of, I'd say, 4 separate parts. So let's just go through them one by one. Here's the oscillator and output section of the ballast. This oscillator section, it's exactly the same as a regular CFL, and like I said, other people have already explained how they work. Then the actual output bit here, we have some slight differences. Here, instead of just one inductor, we basically have 2. We have one that's always active, supplies some current, and we have another one that gets added when the relay closes, which gives a bit more current through the tube. And actually, this first inductor is actually a transformer. It has a secondary winding, which we'll get to. And here's the power input section of the circuit. So it has 3 terminals as a common, a live for low power, and a live for medium or high power. So, start with the actual circuit. We have a common, which has a fuse, and the lives have inductors and interference suppression capacitors. For the purposes of discussion, we can just ignore those. So what's interesting here is the circuit works a bit differently depending on which hot wire is active. If the lamp's on low, there's 120 volts AC across S1 and S2. And if we look, they just go and feed into a full bridge rectifier, which charges up this string of capacitors to about 160 volts DC. And then, yes, it's covered up a bit. These 2 high value resistors will distribute the charge and make sure that, one doesn't get all the voltage. And those will also make sure that the capacitors bleed away their charge when power is unplugged, which would help for safety. But now, what happens if power is applied between S1 and S3, if the lamp's on medium? What happens is, basically, S3 comes here, and with 1 half cycle, S1 is about 170 volts higher than S3. Then current flows through a quarter of the bridge rectifier and charges up the top capacitor. And then on the other half cycle, when S1's lower, how does that work? The current flows and charges the bottom capacitor. So they'll each end up charged to about 160 volts for a total of around 320 volts. That's interesting. And then if both low and high are powered, then low is always the same voltage as high, which is in the middle, so none of these diodes conduct and the low contact isn't used. So then that covers basically how we get more output from switching from low to medium, because it increases the power supply voltage. And then the next puzzle is just how does it switch from medium to high. So now the only part of the schematic left is the part that activates the relay. So let's start with the simple end of it. So we had our current limiting inductor with the extra tap, with the extra winding on it. And that winding's here. And then it charges up this capacitor. So that's that. And then here is the relay coil itself and a back EMF protection diode. It's driven by a little NPN transistor. And if we follow its base, so we have a 30K resistor, and then we have a filtering capacitor, 4.7 microfarads, with a discharge resistor. And I should say, this negative rail is the same negative rail as the rest of the circuit. And coming from here is the power input for when it's in low. So let's start when it's in low. So basically, every cycle this goes negative, this goes to the 0 volt rail. So then any charge that was in this capacitor gets discharged through this. And then, because it can't charge up enough, the transistor stays off. That's one scenario. So then if the lamp's on medium, the power just comes in here, and the low power contact is disconnected. So because it's disconnected, it doesn't charge, this line doesn't provide any current, so then this 100K resistor discharges the capacitor, keeping the transistor off. And of course, the last scenario is when the lamp's on high. In that case, power is on both S2 and S3. And not only is power on both of them, they're tied together. So as we discussed earlier, when it's operating in medium or high, it's like a doubler. So each capacitor has 160 volts. So this point here is 160 volts above the negative rail. And because these two contacts are tied together, that means this is also at 160 volts above the negative rail. So then that 160 volts goes through this 220k resistor. It can charge up the capacitor, and then that can drive the transistor, turning on the relay, which then closes the contact and allows more current to flow through the circuit. And that's how that works. Now I think just to better demonstrate, I'll try showing you some measurements of the circuit when it's actually powered. I just soldered some wires to some, I'll say, key areas of the circuit board. I have these black and yellow are across the main power supply capacitors, and this green is connected to the base of the transistor controlling the relay. Okay, here's my precarious test setup. I have the ballast screwed into the lamp and two multimeters hooked up. The analog multimeter is connected to the main power supply of the ballast, and the digital one is showing the voltage on the base of the relay driving transistor. This is a 2-volt scale, and this should be a 500-volt scale. What I'm expecting is, when you put it on low, we'll see about 1/3 of the way on here and nothing here. Put it on medium, I expect 2/3 and nothing. And then on high, I expect 2/3 and about 0.7. Now, I haven't cheated. This is actually my first time trying this. So if anything goes wrong, it's going to be on camera. Okay. Plugging it in. Okay, it's off. I'm going to switch to low. That's not right. I see. I forgot to move my probe, so it was actually on the 125 volt. Now let's try again. So it's already on low. I guess it should see 1/3 deflection. That's about what we have here. I was expecting 0 here, but like 1/4 of a volt is fine too. It's still not enough to turn on the transistor. Now I'll switch this to medium. We should see the analog one jump to 2/3, and this should stay about the same. Okay, this jumped up. To get the actual number, it looks like a bit over 300. And this is showing, like 0.35 volts-ish. Again, more than I was expecting, but still not enough to turn on the transistor. I should keep in mind I still haven't changed the battery in this, so its reading is a bit higher than it actually is. Now, I'll switch this from medium to high. Should see high voltage on the base. 0.68 volts. That should be enough to turn on the transistor, and it would activate the relay, except there's no current flowing, so that supply isn't active. And just show this one more time. Off. Low. You see, there's still some voltage there. When I went to low, it immediately dropped. Low. Medium. High. So, there you go. That's the circuitry inside this three-way compact fluorescent light ballast. Hopefully you liked what you saw here. If you did, be sure to like, subscribe, comment, and share. See you next time.